Hi and welcome to this video on sequences and series. In an arithmetic sequence we have a list of numbers or terms, say 1, 4, 7, 10 and 13, and when we subtract one term from the previous term there is a common difference. In a geometric sequence we have again a list of numbers 1, 2, 4, 8, 16 and so forth, and if we have a look between the second number and the previous number, or the third number and the previous number, there is a common ratio. Right. For series we have the same list of numbers, but we have 1 plus 4 plus 7 plus 10 plus 13, and the same in the geometric series we have 1 plus 2 plus 4 plus 8 plus 16. Now what do we mean by common difference? So in the arithmetic sequence, when we take the difference between the two terms, that term and the previous term, or the third term and the previous second term, we get the same difference. So we would have, here we would have a difference of 3, so that's plus 3. Here we would have a difference of 3, so that's plus 3. Here we would have a difference of 3 plus 3. So the common difference D equals 3. In the geometric sequence we divide the second term by the previous term, or the third term by the previous term, or the fourth term by the third term. So what we get is a common ratio, and in this case 2 divided by 1 is 2, 4 divided by 2 is 2, 8 divided by 4 equals 2. So the common ratio R equals 2. Okay, so let's have a look at another arithmetic sequence. So 15, 10, 5, 0, minus 5. So if we have a look at this, we're going down in 5s. So there's a difference of minus 5. There's a difference of minus 5 between each term. So the common difference D equals minus 5. And our series in this case is 15 plus 10 plus 5 plus 0 plus minus 5 and so on. In this case, if we have let's have a look. Let's have a look at a plot of the number of term. So that would be the first term, the second term, the third term, the fourth term, plotted against the value of the term. So like for instance here the first term would be 4. So the first term would be 1, and then we would have a difference of 3, we go to 4. On the third term would be 7, we'd have a difference again of 4. We would get a straight line relationship. In the geometric sequence, if we plot the term number against the term, we wouldn't get a straight line, we would get something like, so the first one would be 1, the second one would be 2, the third one would be 4, so we get a curve. If we have a look at the arithmetic sequence, 8, 12, 16, 20 and so on, and we want to know the common difference, we take away 12 from 8, which gives you 4, 16 minus 12, again 4, 20 minus 16 is 4, so the common difference D is 4. A sub 1, which is the first term, is 8. A sub 2, which is the second term, is 8 plus 4. A sub 3 is 8 plus 2 plus 4. A sub 4 is 8 plus 3 plus 4. So A sub n, which would be the nth term, is 8 plus 4 and then n minus 1, because we notice that on the third term this is n minus 1, and in the fourth term this is n minus 1. So the general term formula which you must learn is A sub n. The nth term is the first term, A sub 1, plus the nth term minus 1 multiplied by the difference. Looking at the arithmetic series, 8 plus 12 plus 16 plus 20 and so on. If we write the sum of terms, so that would be 8 plus 12 plus 16, as S sub n, we get 8 plus 12 and so on until we get to 4n and then 4n plus 4, 4 being the difference between the terms. So the difference is still 4. Now if we do this sum of terms again, but we reverse this order underneath, so this one would be 4n plus 4, underneath here would be 4n, and then carry on, and underneath here would be 12, and under here would be 8. When we add these two together, so 2, each pair here, so we're going to add each pair together. Let's make this more distinct. So 8 plus 4n plus 4, then 12 plus 4n, 4n plus 12, and this. So we're going to add each pair. So each pair equals 4n plus 12. So that's 2 s, which is the sum of the terms. 2s sub n is n 4n plus 12. This then equals 4n, n plus 3, and then when we divide by 2, just to get the sum of the terms, because we had 2 here, let's put that in brackets if you want to make that more clear. So just just the sum of terms, we divide this term by 2 and we get 2n, n plus 3. So this is another formula that we need to know, and usually we know it in the form of when we know the first term and the last term. When we know the first term and the last term, the sum of terms, s sub n, equals n, the first term, plus the last term, over 2. If we have the arithmetic series again, we can write the sum of terms, s sub n, as a, and then the second term as a plus the common difference. The third term becomes a plus twice the common difference, and then the nth term is a plus n minus 1 times the common difference. If we reverse the order underneath, then the sum of terms, this would become a, which is the last term here, plus n minus 1 d plus a plus n minus 2 d, and so forth. When we add these two terms, each pair then becomes, so this is 2 multiplied by the sum of terms, so 2Sn equals 2a plus n minus 1 d plus 2a plus n minus 1 d again, and so on. So 2 or twice the sum of terms equals n 2a plus n minus 1 multiplied by the common difference, and when we divide by 2, the sum of terms is n over 2, 2a, which is the first term, n minus 1 multiplied by the common difference. If we put this in a form that you need to remember, it's this one, so that we need to remember. And also this can be written as sum of terms equals n over 2, a, which is the first term, plus l, which is the last term. So that's another way to remember that formula. But the one in the highlighted red is the sum of terms when you know the first term and common difference. Geometric sequence we said was something like 1, 2, 4, 8, 16 with a common ratio. In this case the common ratio we get by dividing 2 by 1, or 4 by 2, or 8 by 4, and the common ratio R is 2. Geometric series are the same set of numbers, but 1 plus 2 plus 4 plus 8 and so on. If we want to find the nth term in this case, we have a sub n equals the first term multiplied by the common ratio to the power n minus 1. So that's the formula you need to remember for this, for geometric sequences. And then for the sum of terms, S sub n, it's the first term, a sub 1, 1 minus r to the power n over 1 minus r. So that's the formula you need to remember for the sum of terms for a geometric series. This can also be written as S sub n, which is the sum, first term, Rn minus 1 over R minus 1. These two are the same, depending on what kind of geometric sequence we're dealing with. With an infinite series, which is r is less than 1, s equals a sub 1, which is the first term, 1 minus r. Okay, let's have a look at using the general term formula. So in this first case we have to find the 21st term and sum to 24 terms of the series 2, 4, 6, 8. So first of all, let's make sure this is an arithmetic series, and how we do that is to make sure that there is a common difference. So 4 minus 2 is 2, 6 minus 4 is again 2, so that shows that there is a common difference, and this is an arithmetic series. Now the first term, a sub 1, is 2, and the common difference, as we just discussed, is also 2. So our 21st term, a sub 21, equals a sub 1, which is 2 multiplied by, or plus, sorry, our term, which was 21 minus 1, which is 20 multiplied by 2. So 20 times 2 is 40, plus 2 is 42. So our 21st term is 42. Now let's have a look at our sum of terms to the 24th term. So S 24, this would equal 24 divided by 2, and then our 2 multiplied by 2 plus 24 minus 1, and our difference again, which is 2. So this equals 12, and that's 4 minus 46, and that equals 600. So those are our two answers, 600 and 42 in the top case. Question, first of all, let's make sure it is an arithmetic series with a common difference. So we can see that when we subtract 5a, take away 3a, we're left with 2a. 7a, take away 5a, again is 2a. So our common difference D is 2a. Now we need to plug everything into our formula. So the sum of the series is 624a. So 624a equals n over 2 6a plus n minus 1, and our difference, which was 2a. This then 624a equals 6a plus 2an minus 2a, which is 4a plus 2an. Then when we divide by 2 and divide by plus n and then divide by a, we're left with 624 equals 2n plus n squared. Yep. So that was 624. This worked out as 2an plus an squared, and then when we divide by a, we get 2n plus n squared. That's right. So now we have this in terms of a quadratic. So n squared plus 2n minus 624 equals 0. So when we factorize, we get n plus 26 and n minus 24. So each of these is equal to 0, which means n is actually minus 26, or n equals 24. So minus 26 isn't an option, so the answer is n equals 24. I'll look at another similar question. So in this case we've got the sum S of n equals 396. So again, when we plug that into our formula, we get n over 2 multiplied by 1 plus n minus 1, and the common difference here is 7 equals 396. When we get rid of this 2, get n2 plus n minus 1 multiplied by 7 equals 792. Then n2 plus, get rid of these brackets, 7n minus 7 equals 792. N 7n minus 5 equals 792. Then when we get rid of these brackets and make it equal to 0, we get 7n squared minus 5n minus the 792 equals 0. Factorizing, we get 7n plus 72 and n minus 11 equals 0. So here we have n is minus 72 over 7, or n equals 11. So the negative is not an option, and the answer is 11. In this, we're asked to find the sum to 20 terms. First of all, make sure it is an arithmetic series. So 9 minus 5 equals 4. So 13 minus 9 again is 4. So the common difference D is 4. So we want sum to 20 terms. The first term is a sub 1, which is 5, and the common difference is 4. So the sum to 20 terms is 20 divided by 2, 2 multiplied by 5, plus, and then it's n minus 1, which is 19, and we multiply that by the common difference, which is 4. And this, when we work it out, gives us 860. And that is your answer. I'm going to have a look at geometric sequences now. So we have to find the sum of this term to the 11th term it's going to be. So a sub 1 is 4, which is the first term. R, which is the common ratio, is 6 divided by 4, which is 1.5. And then the number of terms we're going to go to is the 11th term, which is 11. So our S11 would equal 4, 1.5 to the 11 minus 1 all over 1.5 minus 1, and this equals 684 to 4 significant figures. Another similar question, geometric sequence, find the 26th term. So first of all we need the first term, which is a sub 1, which is 8. The common ratio, which is 6 divided by 8, which is 0.75, and then the term we want up to is the 26th term. So we have S, the sum up to the 26th term equals 8, 1 minus 0.75 to the 26 all over 1 minus 0.75, and that is 31.98 to 4 significant figures. Series and sequences are sometimes used to calculate interest per annum. So if we have a starting capital of £5,000 in the bank, how many years will it take to exceed 10,000 with the interest rate at 6% per annum? So here we have after n years, capital sum will have grown £5,000, which is what we initially started with, times the interest rate of 1.06, 1.06, and n. So therefore 5,000 1.06 to the n is greater than 10,000, which implies that 1.06 to the n is greater than 2. So taking logs on both sides, we have n natural log 1.06, so we bring the n down using log laws, is greater than natural log of 2. n is greater than natural log of 2 divided by natural log 1.06. Therefore n is greater than 11.9. Therefore it will be 12 years before the investment doubles. Okay, we're going to have a look at sigma notation. Now this symbol sigma can be considered as representing the sum of. So if we have the series, two plus 4 plus 8 plus, I'm going to go up to 2 to the 12, we can write this in shorthand using this sigma as r equals 1 as the lower limit, 12 as the upper limit, and then our general term would be 2 to the r. So we have 2r is the general term, r equals 1 is our bottom limit, and our 12 is our top limit. Okay, so let's have a look at a half plus 2/3 plus 3/4 and that would continue until we get to 99 over 100. So our general term would be r over r plus 1. Our bottom limit would be 1, and our top limit would be 99. So we'd write this as r equals 1 to 99 r over r plus 1. Another way of writing this would be if we had r equals 2, then this would make our upper limit as 100, and our general formula or our general term would be r minus 1. So 100 minus 1 would be 99 over r, which was 100. So these two are equivalent. Now let's have a look at this one, which is the top limit is 9, the bottom limit is 1 of 10 minus r squared. So this is nothing but 10 minus 1 squared plus 10 minus 2 squared, so forth. This equals 9 squared plus 8 squared, and then plus going up to 1 squared. So another way of writing this would be, so an alternative, we could write this as r equals 1 to 9 of r squared. Okay, so we've been talking about the general term, so let's have a look at that. So in this series, 2 plus 4 plus 6 plus 8 and so on, every integer is divisible by 2. So the even integers we can write as 2r, where r is some integer. So the odd integers, 1 plus 3 plus 5 plus 7, where the sum is represented by sigma, that can be written as 2r minus 1. Or sometimes 2r plus 1. So an even integer is written as 2r, and an odd integer as 2r minus 1 or 2r plus 1. So if we have something like, let me have a look, the top limit is 7 and the bottom limit r equals 1 of 2r minus 1. This indicates the sum of 7 terms, and the range is from r equals 1 to r equals 7. So r minus 1 would be the odd integers. So let's have a look at that. So that would equals 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. So that's 1, 2, 3, 4, 5, 6, 7, and when we get the sum, that equals 49. Okay, let's have a little practice with sigma notation and the general term. So in the series 2 plus 4 plus 6 plus 8 and carrying on, the general term, as we discussed before, was 2r, and the sum of the first terms can be written as r from 1 to 10 of 2r. Okay, the second one, 1 plus a half plus a third plus a quarter. The general term is 1 over r, and the sum of the first terms, r equals 1 to 10 of 1 over r. 1 plus 8 plus 27 plus 64, 2 cubed, 3 cubed. So we're looking at the general term as r cubed. Some of the first terms, 10 terms, would be from r equals 1 to 10 r cubed. Okay, here we're looking at minus 1 and then 2 plus minus 3, then 4, then minus 5. So we've got a negative 1 somewhere in the general term. So the general term is minus 1 to the power r. So the sum of the first 10 terms then becomes from r equals 1 to 10 minus 1 to the power r. In this one, the general term is 1 over r factorial, and the sum of the first 10 terms becomes, we've got a 0 to begin with, so r equals 0 to 9. That'll make the first 10 terms, and it'll be at 1 over r factorial. Sometimes we find sigma notation where the sum is required to n terms, so that would be from r equals 1 to n, say of r squared. This would equal, from starting from 1, which is our bottom limit, 1 squared plus 2 squared plus 3 squared plus, and so on until we reach n squared. So let's have a look at these going up to n terms. So 5 over 2 plus 5 over 4 plus 5 over 6 plus 5 over 8. So the general term is 5, and the denominator is going up 2, 4, 6, 8, which is 2r. So this then becomes r equals 1 to n or 5 over 2r. And this b, 1 over 1 plus 1 over 3 squared plus 1 over 5 squared. The general term is 1 over, and we've got odd numbers underneath, which is 2r minus 1, and we're squaring them. So this then becomes r equals 1 to n 1 over 2r minus 1 squared. Okay, and that pattern continues. So we just have the sum, or sigma, with the bottom limit and the top limit, and then our general term. So for these, I'll just write the general term, and you can work out what it looks like with the sigma notation. So the general term here, 2 minus 4 plus 6 minus 8, continues, with minus 1 because we're alternating, and then r plus 1, and then because they're even numbers, 2r. Here we have the general term again, alternating minus and plus, so minus 1 to the r, 3r. Here we have the general term minus 1 to the r. Okay, here we're going to have a look at two rules when we're dealing with sigma notation. So rule number 1. So if we have f of r as a general term, and k is a constant, then we write the sum of r from 1 to n, the constant k, and then the general term f of r. Then we can take the k and factor it out of sigma, so this becomes k sigma r equals 1 to n f of r. So constant can be factored out. When f of r equals 1, then this sigma equals n equals 1 to n of k. So we get k being factored out, r equals 1 to n of 1, and this equals k 1 plus 1 plus 1 up to n, and this equals k of n. Rule 2. So we have if f of r and g of r are two general terms, then if we have the sum of them together, so that will be r equals 1 to n, and we're adding those two general terms, so that will be f of r plus g of r, then we can do that by splitting them, which would be r equals 1 to n fr plus r equals 1 to n g of r. A quick look at those two rules we've just discussed. So we're going to find the sum of r equals 1 to n 6r plus 5. So we can, using rule 2, we can split this into 2, so this becomes the sum of r equals 1 to n of 6r plus r equals 1 to n of 5. Here we've got a constant, so we can take that outside using our rule 1. So this becomes 6 r equals 1 to n r plus r equals 1 to n 5. This equals 6 n plus 1 over 2 plus 5n, which in turn equals 3. When we get rid of the 2, get rid of the brackets, n squared plus n plus 5n. And then finally, tidying up, we get 3n squared plus 8n, which is n 3n plus 8, when we take the n outside the bracket, factor out the n. The sum of natural numbers. So if we had the sum from r equals 1 to 6, that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we wanted to find the sum of that. How we can do it is we can add the 6 and the 1, the 2 and the 5, the 3 and the 4, and in each case we get a 7. So this would be 3 times 7 equals 21. Now if we take a similar approach to the sum of r equals 1 to n, so we have 1 plus 2 plus 3 plus 4, and then so on. And if we take a second set, so if this would be our first sum of numbers, and if we take our second sum of numbers and we do the reverse, so right at the end we would have our n. Next to that, the next number along going backwards would be n minus 1. Going backwards again would be n minus 2, n minus 3. So we've got 1, 2, 3, 4 terms there, 1, 2, 3, 4 terms there. So now what we were to add these two together, so we would add the n to the n plus 1, 2 to the n minus 1, 3 to the n minus 2, and 4 to the n minus 3. In each case we would get n plus 1, n plus 1, n plus 1, n plus 1. Now we've got two groups, which is 2Sn, and each group is n plus 1, so it's n and then multiplied by n plus 1. So our sum would then equal n plus 1 over 2. And then another way of writing that is n squared plus m over 2. In this question we're going to have a look at the geometric series and finding the nth term when we're given two terms. So here we're asked to find the 10th term, and we're given that a sub 5 is 96 and a sub 7 is 384, and we have to find a sub 10. So basically what that means is we've got a sequence, we've got a series, so we've got 1, 2, 3, 4, 5. So our fifth one, a sub 5, is 96, then we've got a space, then our seventh one is 384, and then some other numbers. And we want to find a sub 10. So the formula we're going to use for geometric series is a sub n equals a1, which is our first term, and that's multiplied by r, which is our common ratio, and that's to the power of n minus 1. So how do we do this? Well, let's make two equations first. So our first equation will be using this a sub 5, which is a sub 5 equals a sub 1, which we don't know, the common ratio, which is r, and n minus 1 will be 5 minus 1, which is 4, and that equals 96. We'll call that equation 1. And then similarly we have a sub 7 equals, again, the first number, a sub 1, which we don't know, the common ratio, now to the power 6, equals 384. We'll call that equation 2. Now divide 2 by 1, and we get a1 r to the 6, a1 r 4 equals 384 over 96. So our r squared equals 4, r equals plus or minus 2. Now from our equation, which was equation 1, a1 r4 r to the power 4 equals 96, a1 equals 96 over 16, and that equals 6. So now we can put that into our equation. So we get a sub 10 is a1, which is 6, r, which is 2, or plus or minus 2. So we'll just use 2 at the moment. 2 to the power 10 minus 1, which is 9. And this equals 3072. Or, because this could be a minus 2 and it's to an odd power, it could be minus 3072. If we have a look at a recursive formula and the explicit formula, a recursive formula is for an arithmetic sequence and the sequence, obviously because it's arithmetic, has a constant difference. And for a recursive formula we need a first term. So if we have A1 as the first term, and our recursive formula is an equals an minus 1 plus 300. This is the previous term in red. This is our constant difference, or D. So our series, our arithmetic sequence would be, if we knew the first term, would be 100, 400, 700, and so on. This formula only works for n greater or equal to 2. You need to add the constant difference each time. So for example, if we had A1 equals 50, and then our recursive formula was an equals an minus 1 plus 30, n greater or equal to 2. So each term is the previous term, and we add the constant difference of 30. So A1 is 50, A sub 2 is A sub 2 minus 1 plus 30. This is nothing but A1, which is 50. So A sub 2 equals 50 plus 30, which is 80. And similarly, A sub 3 would be 80 plus 30. Using our recursive formulas, you need to write down the individual terms and then find the requested term. So in a recursive formula, each term is used to produce the next term. So for example, if we had a series saying minus 5, minus 2, 1, 4. First of all, what we would do is find out if it's arithmetic or geometric, and we can do this quite easily like we discussed. So minus 2 minus minus 5 is plus 3. 1 minus minus 2 is plus 3, and then that one is plus 3 also. So we can see that it's clearly an arithmetic sequence. The recursive rule for this would be A sub n equals a n minus 1, which is the previous term, plus 3. So that's our recursive rule. So our first term, a1, is 5. So we have minus 5 minus 2, which is another plus 3, 1, 4, 7, 10, and so on until we find the term that we're after. So if we were after, say, the 7th term, so that'd be 1, 2, 3, 4, 5, 6, so the 7th term would be 13. So for the recursive formula, or the recursive rule, we'd have to list out the sequence, whereas in the explicit rule we just use the formula an equals a sub 1 plus n minus 1 d to get the 7th term. Okay, so long as we have a relationship and each term can be used to produce the next term, we can use a recursive formula. So for example, we discussed 2, 4, 6, 8, 10. And so on. The explicit formula is an equals 2n, and the recursive formula, where a sub 1, the first term, is 2, the recursive formula becomes an equals the previous term, which is an minus 1 plus 2. So the same can be said for a geometric sequence. So if we had a geometric sequence, so this one is arithmetic. So if we had a geometric one, say we had 3, 9, 27, 81, then our explicit formula becomes a sub n equals 3 to the power n, and a sub 1 is 3, the first term is 3, so our recursive formula becomes an equals 3 an minus 1. Similarly, another sequence, so this one is not geometric or arithmetic, so this one would be 2, 5, 26, 6, 7, 2. Our a1 is 2, the first term is 2, and our recursive formula becomes an, the first term, an minus 1 squared plus 1. So it's the previous term squared plus 1. I'm just going to go over a quick method of writing the recursive formula if you have any difficulty. So if we had a sequence saying 4, 5, 7, 10, and we wanted to write the recursive formula for that, we make a table. In the first column we have n, in the second column we have t, and here we have the relationship. and the relationship is to the previous number. So here we have 1, 2, 3, 4. So we list 4, 5 as those terms, so that would be 4, 5, 7 and 10. And our relationship to the previous term is 4 plus 1, 5 plus 2, 7 plus 3. So here we can see that the relationship goes the previous number. The recursive formula is an equals the previous number plus n minus 1. So if we were here, it would be 2 minus 1, which is 1, 3 minus 1. Okay, so let's have a look at another one. So if we had 3, 6, 12, 24, which is geometric, we go make our table, n, t, and then the relationship. So our n would go 1, 2, 3, 4. Terms goes 3, 6, 12, 24. And our relationship is 3 times the previous term 2. This is 6 multiplied by 2. This is 12 multiplied by 2. So our recursive formula is an, where a1 is 3. An equals twice the previous term. Let's have a look at one slightly more difficult. 1, 5, 14, 30 and so on. Let's make a quick table. N, term and relationship. Relationship to the previous term. So we have 1, 2, 3, 4 numbers. Terms are 1, 5, 14, 30. And the relationship to the previous one is 5 is 1 plus 4. 14 is 5 plus 9. 30 is 14 plus 16. So we're looking at the previous term and how we get to the actual t. So when we look at this, this is an equals the previous term, which is an minus 1 plus. Now 4 is nothing but n squared. 9 is 3 squared. 16 is 4 squared. So that's plus n squared. It's a special sequence now. So this is 0, 1, 1, 2, 3, 5, 8, and this is called the Fibonacci sequence. And what the Fibonacci sequence is that number is the sum of 1 and 0, 2 is the sum of 1 and 1, 3 is the sum of 2 and 1, 5 is the sum of 3 and 2. So it's the sum of the previous two numbers. So in this case we want the first number, a sub 1 is 0 and a sub 2 is 1. So we need to know the first two numbers, or the first two terms, and then an equals the previous term, an minus 1, plus the term before that, which is an minus 2. Okay, a quick look at another sequence and then looking at the recursive formula. So we have 2, 5, 11, 23. Draw our table. Number, term, relationship to the previous. 1, 2, 3, 4, 2, 5, 11, 23. So this one would be 2 plus 3, 5 plus 6, 11 plus 12. So our relationship is the previous number, and we add to that the previous number, so that it'll be the previous number, which is 2 plus 1, 5 plus 1, 11 plus 1. So we want the previous number, a n minus 1 plus 1. Okay, the last one, now using this table. So 1, a half, 1/6, 1 over 24, and so on. So we'll draw our table, quick table. Number, term, relationship. So it refers to 2, 3, 4. This is 1 half, 1/6, 1 over 24. So this one would be 1 multiplied by a half. This one would be 1 half multiplied by 1/3. This one would be 1/6 multiplied by 1/4. So our a sub n equals the previous number, a n minus 1, and then we have to multiply it by 1 over n. So this is 1 over 2, which is n, 1 over 3, which is n. And this can also be written as an minus 1 over n. Okay, here we're going to look at whether a sequence converges or diverges. We say a sequence converges if a limit exists as a real and finite number. And a sequence diverges if this limit is infinity or doesn't exist. So what do we mean by that? So if we had a sequence a sub n equals n plus 2, so if we write out the sequence, that's 1/3 when it's 1, 2 over 4 when n is 2, and similarly 3 over 5, 4 over 6, and so on. So how do we know this diverges or converges? So we calculate the limit as n gets infinitely large. So limit as n tends to infinity, and what that does is if we replace that with x, so So if we had this as x as a variable over x plus 2, we're interested in this relationship, the ratio of the coefficients. And as these two get infinitely large, this becomes 1, so the series converges to 1. What if we had a sub n equals 5? Well, then the series would be 5, 5, 5, and so on. The limit as n approaches infinity would then be 5. So this converges to 5. We can think of a sequence as a function. So if we have f of n equals a n, and we look at f of x, which is the continuous case, then when f of x is a continuous variable, we can look at the limit L. So when f of x is continuous, we can look at L to see if it converges or doesn't converge. So let's have a look at that. So if we have 1 over n, this is 1, 1/2, 1/3, and so on. So our f of n is 1 over n. Our f of x is 1 over x. So the limit 1 over x as x approaches infinity is 0. Therefore, we can say that 1 over n converges. Sequence n over 2n minus 3. So this would be minus 1, 2, 1, and so on. So we want to know, does it converge or does it diverge? So we look at the limits as n approaches infinity. Of n to n minus 3. And then we see the ratio of the coefficients is 1/2. Or we could look at when n is infinitely large, we have infinity over infinity. And using L'Hospital's rule, for limits where we have 0 over is f of x over g of x, this equals 1/2. So it converges to 1/2. Okay, let's have a look at an example where it diverges. So if we have minus 1 for the n, this would give us minus 1, 1, minus 1, and so on. So when n approaches infinity, we have two cases where it goes to either minus 1 or 1. This is when n is odd, and this is when n is even. So we get the sequence divergence, so we say diverges.